Cheaters, Super Mario, John Carmack, and Mortal Kombat. They all have something in common. Using a technique so complex and powerful, it was essential for these titles. Yet, so basic, anyone can harness its potential, manipulating an unseen hero in video game graphics. I'm of course talking about the Stencilbuffer. The backbone to these, many more techniques and graphic illusions. But to grasp how any of these works, we first need to look under the hood and get to know the Stencilbuffer. In this video, we'll cover what the Stencilbuffer is, how it can be used, and why we even use it, as well as DirectX and OpenGL implementations. And because there's so much to cover preemptively, be sure to stick around to the end of the video, because I will reveal a lot of different stencil tricks used in modern games. Well, first of all, what even is a Stencilbuffer? You can think of the Stencilbuffer as a texture with numbers assigned to each pixel. It's usually stored in the depth buffer texture as an 8-bit channel. This means it can only store values from 0 to 255, but the stencil is a bit mask, so we just have 8 unique variables that have the combination of 255. Just assigning a value to a texture is pretty useless if we don't have something in the pipeline that we can use to test it with. That's where our depth stencil state comes into play. Let's say we render a cube to the Stencilbuffer with a value of 1. Or in bits, that would be the first bit enabled. We then proceed to render a sphere that reads from the Stencilbuffer, and it only goes through if the stencil that it's currently on is equal to 1. That will create a mask where the sphere is only visible on top of the cube. And this is what we call a mask. When rendering, each object can read from the stencil, but it can also write to it if certain conditions are met. This enables us to do things like outlines, holes in geometry, stencil volume shadows, decals not rendering on top of certain things, a cool portal effect, because we definitely haven't seen enough of those, and of course the X-ray effect. The stencil test consists of 4 parts: the current stencil value, the comparison value or ref value, the comparison function, and the condition if the comparison is or is not met. You have a lot of different combinations you can choose from in the what to do if this condition is met part. You can example do one operation if the stencil test passes and another one if it fails. Quick general thing to note is that the stencil test always comes before the depth test. Let's talk a little bit about implementation. Before mentioning graphics API specifics, let's just focus on the general purpose of how they work. We have the current stencil value, which is a value between 0 and 255, or a combination of 8 bits, and the same goes for the read value. And the comparison function, which can be never, always, not equal, equal, greater, lesser, greater equal, or less equal. We can also of course set the write value, which is the value we want to write to the Stencilbuffer if certain conditions are met. And for these operations we can set 3 different cases. If the stencil condition fails, if the stencil condition passes but the depth does not, and if the stencil test passes and the depth does as well. And the operation we can apply to these 3 different variants are 0, which is we set the current stencil value to 0. 1, which is the same but we set it to 1. We have replace, which is the big one here because it replaces the stencil value in the current Stencilbuffer with the value you have in your write value. Keep, which is another important one, which is just leave the stencil as it is and do nothing. We have increment, increment wrap, and increment saturate. So increment is just taking the current stencil value and adding on 1 bit to it. Wrapping, not to be confused by the music genre, is when we reach the max value, we wrap back to the min value. And we have saturate, which you might know from HLSL, but it's when we clamp something so that it cannot go above the max value or below the min value. We also have the decrements, and the same with the increments. We have decrement wrap, and we have decrement saturate. And the last one we have is invert, which just takes the bits and inverts them. So if you have 0, 0, 0, 111, it will be 111000 instead. And we need to make sure that we actually create the depth buffer with the stencil buffer in mind, and or enable it as well in the graphics API. Now this is a lot of information, but bear with me. I'll go through how to do this with both DirectX and OpenGL. So if you didn't really follow along, it's fine, because this will kind of be a recap, just a little bit more code based. When using the stencil buffer in a graphics API, there are three main steps to take away. Making sure our depth buffer has enough space for the stencil buffer to also exist in the same texture. We do this by changing how we create our depth buffer. So in DirectX we call create texture 2D and create depth stencil view with our D3D11 texture 2D description and our D3D11 depth stencil view description. With this we change our format from D32 float to D24 unorm S8 uint. So we have essentially just decremented the depth with 8 bits, and the free 8 bits that are left now we use for the stencil buffer. The equivalent in OpenGL. In our GL text image function, we replace GL depth component 32 with the GL depth 24 underscore stencil 8, which does the same but in OpenGL. Or if we don't use GL text image, we can do the same but in the GL frame buffer render buffer. And with the buffer correctly created, we need to make sure that we clear the buffer each frame. In DX11, we make sure the last parameter in clear depth stencil view is set to 0x00, which is just the hex code for 0, so you could just put 0 in there. The OpenGL equivalent is adding onto the GL clear function a flag which is GL stencil buffer bit. Or if we just want to clear the stencil buffer, use GL clear stencil with the same here, the hex value of 0. Now onto the chunky part of it, which is the stencil testing. In DX11 we have a depth stencil object which we pass around and bind when we want to use the stencil testing. And let's configure that correctly. The first part is enabling stencil test. In our depth stencil description, we set our stencil enable to true. The steps are almost identical in OpenGL, with the biggest difference that we don't have an object for it. So the equivalent in OpenGL is GL enable GL stencil test, which is just so much simpler. The next thing we can do, if we need it, is setting the right value. In DirectX, on the description, we set the stencil right mask to the desired bit we want to write to. And in OpenGL, we call the GL stencil mask function and pass in the desired bit. And the next step is where the different graphics APIs actually split up a bit. As we saw before, DirectX has an object that encapsulates all these, and it's done in multiple lines. But OpenGL just does this in one function. So I will show you the OpenGL implementation first. In OpenGL, we call the GL stencil func. The first parameter we pass in is the stencil func, which is, for example, GL equal. The next parameter we pass in is the reference or read value. And the last parameter we can send in is the mask. In DirectX, this is equivalent to setting the description's depth func to, for example, comparison equal, and the description's stencil read mask to our desired read mask. And here is where it becomes a bit confusing, but bear with me. In the GL stencil func, the third parameter mask is actually something that we do not have in DirectX. It masks out values in the current stencil value, but also in the read value or the ref value. And here the other way around also applies, because DirectX has something that OpenGL does not, which is when calling om set depth stencil test, we pass in a stencil ref. The stencil ref is just like the read value, but it applies after the normal read value and stencil value calculation. So after the operation has been done and there is a result, the stencil ref comes in and does the same operation once again, but instead of having the read value, it does it with the stencil value. I know it's a bit confusing, and to be honest, I've never used it, but I guess it could be used to something. Next up is our stencil operations, which are fairly identical, but OpenGL is simpler, so we just start with that. Here we pass in 3 parameters, which is what we do if certain conditions are met. So the first condition and the first parameter is when the stencil fails. The second one is when the stencil passes, but not the depth. And the third parameter is when the stencil and the depth passes. In DirectX, in the description, we set stencil fail up, stencil pass up, and stencil depth fail up. First of all, there is one operation that DirectX has that OpenGL does not, which is writing the value 1 to the depth stencil. Secondly, in DirectX, we can actually have separate operations for the front face and the back face. So in reality, this is what we actually do when doing the description in DirectX. In the description, we do description.frontface or backface dot stencil fail up, and then the same front face or back face dot stencil pass up, and again the same either front face or back face and the stencil depth fail up. And the same goes for the comparison function. We can have one for front face and one for back face. So in the description we can say front face dot stencil func or back face dot stencil func. So now that we have done this work, let's show some cool effects that we can do with this. Let's start with outlines. We first render our object that we want the outlines on, both to the color, depth, and also the stencil, with a stencil value, let's say the second bit on, which is the value 4. We then draw the object again, but a bit bigger, and this time we check against the value of the second bit, or 4, and if it's not equal to 4, we render the object. We'll have some issues that comes with this, but it generally works quite well. When drawing the bigger object, we can instead draw back faces, which will help us some. And be sure to scale the whole object and not only against the vertex normals, because if we do that, it's fine for spherical shapes, but if we have a cube, for example, the sides become disconnected. Holes in geometry, or a portal effect. Draw your hole shape, example a cylinder, with only back faces and only to the stencil buffer. No depth, no color, and right to the stencil buffer. Let's say the third bit, so the value 8. Draw the surface, for example the floor, and only draw if it's not equal to the third bit. Now let's look at stencil volume shadows, popularized in Doom 3. We first create a shadow volume contouring the mesh from the light's point of view. Draw the front face of the shadow volume. If it passes the depth test, increment the stencil value of 1. Now draw the back face of the shadow volume. If it passes the depth, decrement the stencil value. Enable stencil testing and draw only the light calculations where the stencil is 0, unshadowed. Now a trick that's pretty boring but used a lot is when to and when not to render decals on objects. When drawing, for example, the player, if you don't want decals on them, let's say we write to the stencil buffer of the bit 1, so the value of 1. When rendering our decal projection, whatever shape it is in, let's not draw if the stencil value is 1, so where the player are. And finally, for the coolest effect that everyone showcases in Unity and Unreal tutorials, the X-ray effect. When rendering our X-ray object, let's say a player or a chest that we want to see through the wall, just render it as per usual with the depth, but also with the stencil, and write a stencil value to it. Now we render the X-ray object, the player or the chest, once again, but now we only render it when the depth is less. So we are occluded by something, and the stencil value is the stencil value that we have written to, so the third value, so in this case 8. This enables us to stand half behind the wall and half outside of it, and still being able to render the character on one side and the Stencilbuffer X-ray effect character on the other side. While games use the Stencilbuffer to render player behind walls, Sheet show the skeleton of brutality and come up with ways that we never thought had been done before. It is a forgotten hero amongst rendering. With a situation specific enough and a great way of thinking, the Stencilbuffer is the rescue. It helps us do things more optimized and more logically, and the implementations are fairly similar across different graphics APIs. Just like the Stencilbuffer, There are so many techniques that are out there that just hasn't seen the light of day and people don't know about. If you just knew of some of these techniques, you would have a way easier time in game dev and graphics. That's why I've made an entire video covering over 50 graphics optimizations which are used in modern days today. So be sure to check it out right now.